Welcome! In this session, we'll dive into an interesting problem, N-ary tree level order traversal. Together, we'll explore how to solve it step by step, consider different approaches, and analyze their complexities. Let's get started. In this problem, we are working with an N-ary tree. An N-ary tree is a tree where each node can have at most n children. Our goal is to perform a level order traversal on this tree. This means we want to visit the nodes level by level, starting from the root and moving down, and for each level, we want to collect the values of the nodes from left to right. The input to the problem is the root node of the tree, where each node has two attributes, val, which represents the value of the node, and children, a list of its child nodes. If a node has no children, this list will simply be empty. The output of the function should be a list of lists, where each inner list represents the values of the nodes at a specific level, in their left to right order. Let's illustrate this with an example. Consider the N-ary tree shown here. The root node has a value of 1, and it has 3 children with values 3, 2, and 4. Node 3, in turn, has 2 children with values 5 and 6, while nodes 2 and 4 do not have any children. The output for the level order traversal of this tree would be a list of lists. First, a list containing just the root node value, 1, followed by a list of its children, 3, 2, 4, and finally a list for the children of node 3, which are 5, 6. Breaking it down further, at level 1, we only have the root node, which has the value 1. So, the first list in our output is 1. At level 2, the root node has 3 children with values 3, 2, and 4, so the second list is 3, 2, 4. Finally, at level 3, node 3 has 2 children with values 5 and 6, while nodes 2 and 4 have no children. This gives us the third list, 5, 6. Now, let's look at another example to reinforce this concept. Here, we have a tree where the root node has a value of 10 and 3 children with values 20, 30, and 40. Node 20 has 1 child with a value of 50, node 40 has 1 child with a value of 60, and node 30 has no children. For the output, we start with level 1, which only contains the root node, so the first list is 10. At level 2, the root's children are 20, 30, and 40, giving us the second list, 20, 30, 40. At level 3, node 20 contributes 50, and node 40 contributes 60, resulting in the third list, 50, 60. Now consider the simplest case, where the tree has only one node. In this case, the tree consists of just the root node with a value of 1. The level order traversal would simply return a single list with the value of the root, which is 1. Moving on to the constraints, the tree can have up to 10,000 nodes, and each node value is guaranteed to be between 0 and 10,000. For edge cases, if the tree is empty, meaning the root is null, the output should be an empty list. If the tree has only one node, as we just discussed, the output will be a single list containing that node's value. Additionally, the function should handle trees with varying numbers of children at different levels, as well as large trees with up to 10,000 nodes, efficiently and within the given constraints. To tackle the N-ary tree level order traversal problem, we first need to evaluate potential approaches. A brute force solution involves recursively traversing the entire tree while keeping track of nodes at each level. This can be achieved with a dictionary where keys represent the depth, or level, and values are lists of node values. While this approach might seem straightforward, it comes with some significant trade-offs. First, the recursive nature of the solution means additional space is consumed by the call stack, leading to a space complexity that grows with the tree's height. Time complexity remains O(n), as every node is visited once, but managing level-by-level traversal this way is cumbersome and less intuitive. Therefore, we turn to an optimized iterative approach based on breadth-first search, or BFS. BFS uses a queue to process nodes level by level, which aligns perfectly with the problem's requirements. Starting with the root in the queue, we process all nodes at the current level, adding their values to the result for that level and enqueuing their children for subsequent levels. This continues until all nodes are processed efficiently and systematically. With the BFS approach, the time complexity is O(n), as each node is visited exactly once. The space complexity is also O(n), which accounts for the queue used to store nodes at each level. This approach offers several advantages. It is systematic, avoids recursion overhead, and directly matches the problem's requirement to traverse nodes level by level. Another option to consider is depth-first search, or DFS, combined with level tracking. Here, we traverse the tree recursively, passing the current level as an argument to ensure nodes are appended to the correct levels list. While DFS yields a similar time complexity of O, N, the space complexity is O, H, where H is the height of the tree, due to the recursive stack. However, DFS is less intuitive for level-order traversal since it naturally explores deeper nodes first, making it harder to achieve a clean level-by-level result. Ultimately, DFS was chosen as the preferred strategy because it aligns perfectly with the requirements of level-order traversal. By processing nodes in a clear, level-by-level manner, DFS simplifies implementation and eliminates the need for additional bookkeeping, such as level tracking. The key realization here was that level-order traversal is inherently a BFS problem. Using a queue allows us to process nodes in the exact sequence needed without any unnecessary complexity. Comparing BFS and DFS, BFS avoids recursion overhead and is more intuitive for this problem, though it requires additional memory for the queue. On the other hand, DFS relies on a recursive stack, which can be less efficient and harder to adapt for level-order traversal. Compared to the brute force method, BFS is cleaner, more efficient, and directly tailored to the problem's requirements. In conclusion, BFS strikes the ideal balance between clarity, efficiency, and simplicity, making it the best solution for solving this problem. In this problem, we are tasked with performing a level-order traversal of an N-ary tree. A level-order traversal means we visit all nodes at depth 0, then all nodes at depth 1, and so on, progressing level by level. The challenge lies in systematically traversing the tree while grouping nodes based on their levels. The input to our algorithm is the root node of an N-ary tree. Each node contains two pieces of information, a value and a list of children. If a node is a leaf, its list of children will simply be empty. The output will be a list of lists, where each sublist represents the values of nodes at a particular level. To efficiently implement this, we use a queue. The queue enables us to process nodes level by level in a first-in first-out manner. Each element in the queue will be a tuple consisting of the node and its level in the tree. This allows us to keep track of the depth of each node as we traverse the tree iteratively. In addition to the queue, we also maintain a result list called res, which will store the node values grouped by their levels. To initialize the algorithm, we first create an empty result list, res. Next, we set up the queue with the root node and its corresponding level, which is 0. If the root node is null, we handle this edge case by returning an empty list immediately. Once initialized, we begin processing the queue. As long as the queue is not empty, we dequeue the first element, which gives us the current node and its level. If the level matches the current length of res, it means we've encountered a new level, so we append an empty list to res. Then, we add the node's value to the appropriate level in the result list. After this, we enqueue the children of the current node, pairing each child with its level, which is 1 greater than the current node's level. This ensures that all nodes are processed in the correct order. Using a queue is critical for this algorithm because it ensures that nodes are processed in the exact order they appear at each depth. By storing both the node and its level, we can track the depth of each node without needing recursion, making the approach more efficient. A few key edge cases to consider include an empty tree, where the root is null, which returns an empty list. If the tree contains only one node, the result is simply a single level list containing the root's value. Uneven trees, where some nodes lack children, are naturally handled since the algorithm skips over empty child lists. The algorithm is efficient with a time complexity of O, N, as each node is processed exactly once, and each child is enqueued only once. The space complexity is also O, N, which accounts for both the result list and the memory used by the queue. These characteristics make the approach scalable for larger trees. The two primary data structures used in this algorithm are the queue and the result list. The queue is the backbone of the level-order traversal, ensuring that nodes are processed in a first-in first-out order. This ordering is essential for maintaining the proper sequence of nodes at each depth. The result list, res, is used to store the final output, with each sublist corresponding to a specific level of the tree. By grouping node values by their depth, the result list captures the hierarchical structure of the tree. To better understand the algorithm, consider an example tree with the root node 1, which has 3 children, 2, 3, and 4. Node 3, in turn, has 2 children, 5 and 6, while node 4 has 1 child, 7. This tree structure will demonstrate how the algorithm processes nodes level by level, maintaining the correct sequence in the output. At the start, the result list is empty, and the queue contains only the root node and its level, q equals 1, 0. First, we dequeue 1, 0, and add the value 1 to the first level of the result list. The result becomes res equals 1. Next, we enqueue the children of node 1, which are nodes 2, 3, and 4, all at level 1. Moving forward, we dequeue 2, 1, and add the value 2 to the second level of the result list, updating it to res equals 1, 2. Then, we dequeue 3, 1, and add 3 to the second level, resulting in res equals 1, 2, 3. Node 3's children, 5 and 6, are enqueued at level 2. Afterward, we dequeue 4, 1, and add 4 to the second level, resulting in res equals 1, 2, 3, 4. Node 4's child, 7, is enqueued at level 2. This step-by-step processing ensures all nodes are visited in the correct order. Next, we process the remaining nodes at level 2. Dequeuing 5, 2 adds 5 to the third level, updating the result to res equals 1, 2, 3, 4, 5. Similarly, dequeuing 6, 2, and 7, 2 adds their values to the third level, resulting in the final output, res equals 1, 2, 3, 4, 5, 6, 7. To optimize this algorithm further, we can use a deque, which allows for more efficient popping from the front of the queue. Additionally, we could avoid explicitly storing the level by using a sentinel value to separate levels in the queue. Nevertheless, the algorithm already achieves optimal efficiency with a time complexity of O(n), since each node is processed exactly once, and a space complexity of O(n), due to the memory used by both the result list and the queue. This makes the solution both effective and scalable for N-ary trees of varying sizes. This Python implementation solves the LeetCode problem number 429, N-ary tree level order traversal, using a breadth-first search (BFS) approach. First, we define the node class used to represent each node in the N-ary tree. The constructor accepts a value val for the node and an optional list of children. If no children are provided, the list defaults to empty. In the solution class, the level order method performs the level order traversal. The method begins by checking if the input root is null. If the tree is empty, it returns an empty list since there are no levels to traverse. A deque, double-ended queue, is used to facilitate the BFS traversal. The queue is initialized with the root node. This queue will help us process nodes level by level. The while loop runs as long as there are nodes in the queue. At each iteration, we process all nodes at the current level. The inner for loop iterates over the nodes in the current level, determined by the size of the queue. Each node is dequeued with popleft, its value is added to the current level list, and its children are enqueued for processing in the next level. Once all nodes at the current level are processed, the level list is appended to the result. This process repeats until the queue is empty, meaning all levels of the tree have been traversed. Finally, the result list, which contains a list of values for each level, is returned. This implementation is efficient, with a time complexity of O(n), where n is the number of nodes in the tree, as each node is processed once. The space complexity is O(n), to store the output in the queue during traversal. Here, we start by defining the structure of our N-ary tree. The node class includes an integer value, val, to store the value of the node, and a list of children nodes. We've provided 3 constructors, one default, one that initializes the node's value, and one that initializes both the value and its children. Next, we define the solution class where the level order method will perform the level order traversal of the N-ary tree. This method begins by creating a list of lists called result, which will hold the final output. If the root node is null, there's no tree to traverse, so we simply return the empty result list. This handles the edge case where the input tree is empty. Now, we initialize a queue to facilitate the level order traversal, starting by adding the root node to it. The while loop ensures that we process nodes level by level as long as the queue isn't empty. For each level, we create a temporary list called level to store the values of nodes at the current depth. We determine the number of nodes at this level using queue.size, and iterate through them using a for loop. For each node, we remove it from the queue, add its value to the level list, and enqueue all its children. After processing all nodes at the current level, we add the level list to the result. This process continues until all levels are traversed. Finally, we return the result, which contains the values of the tree nodes grouped by level. Here, we have a simple 3-level N-ary tree to work with. The root node is 1, which has 3 children, 3, 2, and 4. Additionally, node 3 itself has 2 children, 5 and 6. To start the level order traversal, we initialize an empty result list in a queue containing only the root node, which is 1 at this point. At the first level, we process the root. We initialize an empty level list and note that there's only one node in the queue. We dequeue node 1, add it to the current level list, and then enqueue its children, 3, 2, and 4. Finally, we append the level list, which is 1, to our result. At the end of this step, the result is 1, and the queue contains nodes 3, 2, and 4 for the next level. Now, moving on to the second level, the queue contains 3 nodes, 3, 2, and 4. We initialize an empty level list and observe that the queue's length is 3, indicating 3 nodes to process. First, we dequeue node 3, add it to the level list, and enqueue its children, 5 and 6. Next, we dequeue node 2, add it to the level list, and since it has no children, we move on. Finally, we dequeue node 4, add it to the level list, and, like node 2, it has no children. At the end of this level, the level list is 3, 2, 4, which we append to the result. The result now becomes 1, 3, 2, 4, and the queue holds nodes 5 and 6 for the next level. For the third level, the queue has 2 nodes, 5 and 6. We repeat the process, initializing an empty level list and noting the queue length is 2. We dequeue node 5, add it to the level list, and since it has no children, we move on. Then, we dequeue node 6, add it to the level list, and likewise, it has no children. The level list, 5, 6, is appended to the result, making it 1, 3, 2, 4, 5, 6. With the queue now empty, we return the final output 1, 3, 2, 4, 5, 6. In the second example, we have a tree with just a single node, 1. We start the traversal by initializing the result list and a queue containing the root node, 1. At level 1, the queue length is 1, so we initialize an empty level list. We dequeue node 1, add it to the level list, and since it has no children, the queue becomes empty. We append the level list, which is 1, to the result. With no more nodes left to process, the final output is simply 1. Finally, we consider the case of an empty tree, where the root is null. In this scenario, the queue is initialized as empty right from the start. Since there are no nodes to process, we directly return the result, which is an empty list. The time complexity of the N-ary tree level order traversal is O(n), where n represents the total number of nodes in the tree. To understand why, let's break it down. The outer while loop runs as long as there are nodes in the queue, and since each node is added to the queue exactly once during the traversal, the loop iterates a total of n times across all levels. Now, within the while loop, there's an inner for loop that processes all nodes at the current level. For a level with k nodes, the inner loop iterates k times, and across all levels of the tree, the sum of these iterations equals n, since every node is processed exactly once. Lastly, within the inner loop, we dequeue each node, process its value, and enqueue its children. The cost of these operations is proportional to the number of children a node has, but when summed across the entire tree, this still equates to O(n), because every node is processed once. Combining these factors, the total time complexity of the algorithm is O(n). The space complexity of the algorithm is O(n), and this is primarily due to the storage requirements of the queue. The queue's maximum size corresponds to the number of nodes at the widest level of the tree. In a perfectly balanced tree, the widest level is typically the last level, which can contain approximately n/2 nodes, making the queue's space requirement O(n) in the worst case. Additionally, the result list, where all the node values are stored, also requires O(n) space since it holds every node's value in a nested list format. Beyond the queue and the result list, the algorithm doesn't use significant auxiliary space. Variables like level or node consume negligible memory compared to the size of the tree. When we combine the queue and result list, the overall space complexity remains O(n). This algorithm employs a breadth-first search, or BFS, approach, which is particularly well suited for level-order traversal because it inherently processes nodes level by level. This makes it more efficient than a depth-first search, or DFS, approach for this specific task. A naive implementation using DFS might involve recursively traversing the tree and collecting nodes for each level in separate recursive calls. However, this would result in redundant traversals and increased space complexity due to the recursive call stack. In contrast, the BFS approach avoids these inefficiencies by ensuring that each node is processed exactly once and by storing only the nodes at the current level in memory. This makes BFS the optimal choice for level-order traversal in terms of both time and space complexity. When analyzing the best, average, and worst cases, the algorithm consistently achieves optimal performance for level-order traversal. In the best case, the tree is shallow, with only a few levels. Even here, BFS processes each node exactly once, so the time complexity remains O(n), and the space complexity may be lower if the widest level contains fewer nodes. In the average case, which involves a typical tree of moderate height and branching factor, the algorithm still handles O(n) nodes, and both time and space complexities remain O(n). In the worst case, where the tree is highly unbalanced with many nodes concentrated at a single level, each node is still processed exactly once, and the space complexity is dominated by the queue size, which remains O(n). Across all scenarios, the algorithm delivers consistent and optimal performance for level-order traversal. One of the most common mistakes when working with N-ary tree level-order traversal is confusing it with other types of traversals like pre-order or post-order. Remember, level-order traversal strictly processes nodes level by level, which requires a queue for a breadth-first approach. Using a stack instead of a queue can lead to incorrect results because stacks follow a last-in, first-out order, which is unsuitable for this problem. Another frequent error is failing to consider edge cases, such as an empty tree or a tree with just one node. These scenarios often lead to runtime errors if not handled properly. Additionally, memory inefficiency can become an issue when separate lists are created for each level without clearing unused levels, leading to unnecessary memory usage. Proper queue management is also crucial. Forgetting to enqueue all children of a node or accidentally enqueuing null nodes can result in incomplete or incorrect outputs. Lastly, it's important to avoid modifying the list of children during the traversal process. Doing so can disrupt the iteration and lead to skipped nodes or unexpected results. Focus on keeping your data structures organized and your logic robust to avoid these pitfalls. Level-order traversal is essentially an application of breadth-first search, so mastering the mechanics of BFS is key. A queue, which operates on a first-in, first-out principle, is fundamental for ensuring the nodes are processed level by level. This pattern is not just useful for this specific problem but also forms the foundation for solving many related tree problems, such as zigzag traversal or finding the largest value in each row. Recognizing this pattern can significantly broaden your problem-solving toolkit. During an interview, it's often beneficial to discuss the trade-offs between iterative BFS and recursive DFS for similar problems. While iterative BFS is generally more memory efficient, recursive DFS with depth tracking can sometimes lead to cleaner code. Interviewers also appreciate clarity in explanation, so be sure to articulate how the queue structure ensures that nodes are processed in the correct level-wise order. This demonstrates not just your technical skills but also your ability to communicate your thought process effectively. If you want to deepen your understanding of N-ary tree level order traversal, exploring related problems can be incredibly helpful. For example, binary tree level order traversal, which is LeetCode problem number 102, is a simpler variation and a great starting point. Binary tree zigzag level order traversal, problem number 103, introduces additional complexity by alternating the direction of traversal for each level. Another interesting problem is find largest value in each tree row, problem number 515, which builds on level order traversal to identify the maximum value at each level. Additionally, N-ary tree pre-order traversal, problem number 589, focuses on a different type of traversal but helps you understand tree structures and traversal mechanics more broadly. Practicing these problems will not only reinforce your skills but also expand your ability to recognize patterns and adapt your approach to new challenges. There are alternative approaches to solving N-ary tree-level order traversal that you might consider depending on the specific constraints of a problem. One method is using recursive depth-first search with depth tracking. In this approach, you pass the depth level as a parameter and append nodes to the corresponding level list. This can result in cleaner, more elegant code, though it uses stack memory, which can lead to stack overflow for very deep trees. Another option is to use two queues, one for the current level and another for the next level. This simplifies the logic for switching between levels, as you don't need to manually track level boundaries in a single queue. However, it does come with slightly higher memory usage. Finally, there's the option of in-place modification, such as adding markers to the tree to indicate levels. While this can reduce auxiliary space, it's generally not recommended in interviews since the tree is usually expected to remain unaltered. Each approach has its trade-offs, so understanding their strengths and limitations can help you choose the best solution for a given context. Thank you for joining me on this walkthrough. We've covered the N-ary tree-level order traversal problem, analyzed its key concepts, and discussed its implementation. Remember to keep practicing and applying these techniques to similar problems. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!